All right, dude, we are live. What's up, guys? This is Dem Keys, and today we're going to carry on learning about Hugging Face transformers, and we're probably going to be doing a bit of neural network research as well. Something that I want to do just so I can kind of incorporate the neural network architecture studies into the stream. Something that I want to do is maybe dedicate certain streams to studying the architecture, though I don't think it's all going to be done in one stream. I think it's definitely going to take a couple of streams. As in, I don't think any one given architecture. I don't think I'm going to be done with it in one stream. I'm going to be exploring it both off stream and on stream. I'm going to be exploring it before the stream, during the stream, and probably after the stream as well. Unfortunately, I'm only able to stream for, I don't know, around 2 hours, maybe 1.5, maybe two, maybe 2.5. But that's usually the best that I'm able to do for any given stream. So I don't think I'm going to be covering the entirety of any architecture, but definitely wanna try that approach, because yesterday we wrote down a list of things here, and I kind of want to go through this entire list. Hold on. Yeah, there it is. Yeah, so I kind of want to go through this entire list, playing around with feed forward neural networks, playing around with, or well, first learning NLP and then playing around with various NLP related tasks. Also trying to see what NLP related models are available on Hugging Face through transformers or otherwise. I'm pretty sure through transformers there's going to be a fair bit of them available. But even otherwise, I want to see what tools we have available to us. There was also this other thing that I'd seen that I want to try once I get a better understanding of the transformer architecture. Give me a second. Let me pull that up. I don't remember where I had pulled it up. What was it called? Hold on. Sparse Attention. Yeah. Um, Give me a second. I'm just gonna look that up so I can pull it up and then show you guys. There isn't like too much that I can explain about it because I myself don't really understand it, but I just want to show what exactly it is. What was it? What was it called? Let me just do Sparse Attention. Oh, Sparse Attention Transformer. It might be that. Let me try looking that up because there was a post that I'd seen on Threads. Because I follow a bunch of ML and AI people on Threads, and so I'm able to get a fair bit of AI related news, ML related news, and also a fair bit of data science related knowledge. Um, Rather, I should say I'm able to get a fair bit of data science, AI, and ML related news and knowledge. So there was this one thing that had popped up, and I can't remember who it was, but there was an image in the GitHub profile. There was a library that somebody had made that you could use. Um, I think this is it. Let me see if that image is there. This is probably not it because this has not been updated in, what was that thing called, dude? Hold on, let me see if I have it because I think I'd opened it up on my other machine. Uh, give me a second to look it up. I think it was Nano Sparse Attention. Nano Sparse Attention. Yeah, there it is. So I'm gonna transition back and show you guys. So this is something that I want to try out once I have a better idea of the transformer architecture, because I feel like this builds up on the transformer architecture, but I'm not entirely sure. I could be like completely wrong about it, but I still want to finish learning about transformers first, or the transformer architecture first, and then move on to this. It says the simplest implementation of recent sparse attention patterns for efficient LLM inference. Uh, you know what? Let's try asking. Let's try asking Llama. I didn't. I think the reason why my mind was connecting it to the transformer architecture was because attention was mentioned. But let's try asking which one of these tabs was I not using. I think it was this one. Okay. So I recently learned about a technique called Nano Sparse Attention. I'm wondering if this has anything to do with the transformer architecture, or is this its own architecture? Wait, this is interesting. This name is mentioned here. It says nanosparse attention as described in the repository by so and so. The repository was released recently. Like, okay, I don't know when this thing was made. How far back do the commits go? There's 8 commits on this. So safe to say that the repo is like a week old, and this llama model has the information. There's something. Oh, it mentions online. Dude, I need to. Okay, hold up. I need to test something out here. Uh, why am I not able to change the model? Oh, it stopped. You know what? Let me copy this. I think the thing is. I think the thing is stuck. So let's try. So I just noticed online. So there's online, there's chat, and there's instruct, and then there's a couple of other ones. So I'm going to ask the question here. Is it still going? Okay, so this is interesting. This time it didn't bring up the repo. It mentions this thing here. Let's try it again. Yeah, this time it's not mentioning the repo. All right, let me try asking this version of the LN. Oh God, dude, this is just freaking out. Uh, give me a second. Let me just refresh this thing, and then we can carry on. Okay. Um, I'm currently no. How do I phrase this? I'm currently chatting with you are Llama 3.1 Sonar Large 128K online. I've seen instruct and code being mentioned at the end of a model's, no, an LLM's name, but what uh, what what does online and chat mean? Okay, the terms online and chat in the context of an LLM, like myself, do not pertain to wait, what? Like myself, do not pertain to the LLM's capabilities or training data, but rather to the environment and the mode of interaction. Online, this indicates that the model is accessible and interactive. Can you stop scrolling? Okay. This indicates that the model is accessible and interactive through an internet connection. It means the model is hosted on servers and can be interacted with in real time via the internet. Okay, all right, chat. This refers to the interactive interface through which the users can communicate with the LLM. It implies a conversational or dialogue-based interaction where users can ask questions, provide input, and receive responses in a back and forth manner. In summary, online signifies the model's availability over the internet, and chat highlights the act. Okay. Um, so when I see a model named uh, Llama 3.1 Sonar Large 128K online, what does that mean? To break down the name, all right, let's get to the online thing. It indicates that the model is designed to be accessed and interacted with over the internet. Okay, so it signifies that the model is hosted on servers and can be used in real time through an online interface. Okay, so this is not, it's not saying that the model is actually able to look stuff up, or rather that the model has, you know, searching capabilities, which makes it surprising to me that 1 week old data was mentioned in 1 week old data was mentioned in the in this thing. Hold on. Let me try asking. I remember seeing a repo uh, that had something to do with this. Can you talk about that more? I'm purposely being um I'm not sure what to call it. Ambiguous, maybe? I want to see if the LLM gives, oh, there's the name. How did it get the name? The repository you're likely referring to is Nano Sparse Attention by so and so, which is focused on implementing. Okay, this repo has commits going back to 1 week ago. Okay, let's say 2 weeks. Let's say 1 or 2 weeks, just to give an extra window. Going back to 1 or 2 weeks ago. How do you already know about this repo? How did you get the info so quickly? See, because I'm trying to understand how often the model's weights are being updated, or is it not just the weights? Maybe there's some kind of like extra database that's involved where the knowledge is being taken from. Maybe that database is being updated. I guess we'll learn more about how all of that is done once we get into building LLMs. But for the time being, I just need to understand how this is. Okay, so the information I provided about the Nano Sparse Attention repository is not based on real-time data or direct access to the repository itself. Instead, it is derived from words general knowledge about general knowledge about sparse attention mechanisms and their integration into transformer architectures, which are well documented in the field of NLP and machine learning. Okay, but how do you know the name of the person uh, that the repo belongs to? I know the name of the person associated with so and so repo because it's explicitly mentioned in the repository's README. Okay. If give me a second. Okay, I'm back. Sorry about that. I had to just go and check on something, and I'm done with that. Okay, so wait, let me just confirm that the mic is not muted. Okay, we are good. Great. Now Uh, let's carry on interrogating the LLM. Okay, so if the repo was only made public about a week or two ago, then how do you currently have the data on this repo? Um, has your knowledge base, it's going to say yes. If I ask this question, it's going to say yes. Been updated recently? My ability to provide the information, wait, hold on. My ability to provide information about the nanosparse attention repository, despite it being made public only a week or two ago, is not due to real-time updates or direct access to the repo. Here's why. General knowledge. My responses are generated based on general knowledge patterns recognized. No, wait, hold on. Based on general knowledge and patterns recognized from a vast amount of training data up until my last update. While I don't have real-time access to new data or specific repositories, I can infer and explain concepts based on what is commonly known about sparse attention mechanisms and transformer architectures. Who's building sonar? Let me look this up. I think sonar was mentioned here. This could be a specific variant or fine-tuning of the model. In some contexts, models are fine-tuned for particular tasks or domains, and sonar might indicate a model optimized for a specific type of input or task. Though this is less common and might be a custom or specialized variant. If that is the case, oh God, what did I just do? Okay, so I had the wrong keyboard. Let me just fix that. I was picking up my other keyboard and I accidentally hit F5 on it, and it was supposed to refresh the page on another system, but it refreshed it on another system. And anyways, uh, let me look up llama sonar. Uh, I like that. The first post that pops up is something from 6 months ago that someone posted on Reddit. Apparently, they're not happy with Sonar Llama, and they're like, Sonar Llama 3 is really bad. Example in post. Okay, fine. But where is Sonar from? Uh, your model name mentions the word sonar. What does this mean? Which company made and trained you? When was your last update? Okay, the term sonar in the context of your question appears to be confusing due to multiple different projects and tools that use the same name. Here's a clarification. Sonar in AI audio detection, in data analysis, in code analysis. Okay, hold up. This is an open source model. I'm assuming this is an open source model. I could be wrong, but let me look it up. Llama 3.1 Sonar Large. Let's see if this is available on Hugging Face, and let's see if we're able to find it on the hub. I feel like I should specify when I say the hub, because in this case I'm talking about the Hugging Face hub, but usually when people say the hub, they mean a different hub. Okay, Llama Sonar. What was the name exactly? Llama 3.1 Sonar. Okay. Llama 3.1. Okay, so Sonar doesn't seem to be hosted. There are others provided by NVIDIA, Meta, and a couple of others. There's something called Marcel Bins, or maybe someone called Marcel Bins. Yeah, I'm not seeing it here. I'm not sure what sonar is supposed to mean. Let's see if it mentioned, okay, your AI model. Your AI model, however, is not associated with any of these sonar projects. I'm a large language model developed by OpenAI. What? And my knowledge was last updated in October 2023. I don't have real time. Okay, all right. It says llama, but it's mentioning OpenAI. Um, I think this is, I mean, I could be wrong here, but I think this might just be it making up information. But okay, anyways, all right. Let's refresh this and try typing in the question again. Okay, and let's actually learn about the thing. Okay, the technique known as Nano Sparse Attention. It's also uh, worth noting that there's different types of responses each time, even though it's the same text. So I wonder if they're finding a way to introduce variation through some kind of noise, just to add like randomness in the way that the model speaks, or if it's just the way that LLMs work in general, where they won't always give you a one-to-one answer. There's always a chance that it's going to give different, not wrong answers, not different answers, but rather it's going to form the sentences in different ways. That's something we're going to have to kind of explore while building LLMs. Okay, the technique known as nanosparse attention is closely related to the transformer architecture, particularly in the context of attention mechanisms within transformers. The nanosparse attention repository on GitHub provides implementations of recent sparse attention mechanisms that are integrated into the transformer architecture. Here sparse attention is used to optimize the attention process in both the pre-filling and generation steps of large language models inference. The methods implemented, such as local window plus attention sinks, vertical slash attention, block sparse attention, snap KV, and TOVA, are all variations of attention mechanisms designed to reduce computational complexity while maintaining or improving performance. In essence, nanosparse is not a standalone architecture, but rather an enhancement or modification to the attention layers within the transformer architecture aimed at improving efficiency and interpretability. Okay, yeah, aimed at improving efficiency and interpretability. Um, all right. So I also have been, and this is like from a while back, but I kind of want to see if I'm pretty sure it's still a thing, but I need to. Oh, okay. You know what? I'm gonna ask the question. I think I also need to note down nanosparse attention, so I'll remember to look this up. I also have been hearing about something called LoRA. Can you explain what that is? Does it also have something to do with transformer? Uh, did I spell that wrong? Yeah, transformer architecture. Okay, all right. Right. Low rank, low rank adaptation is a technique designed to efficiently fine-tune large pre-trained machine learning models. Okay, particularly those based on the transformer architecture without the need for extensive retraining of the entire model. Key concepts: efficient fine-tuning. LoRa allows developers to adapt large pre-trained models to new tasks or datasets by modifying only a small subset of the model's parameters. This is achieved by introducing low-rank matrices into the model architecture rather than adjusting all the parameters of the original model. Wait, this is achieved by introducing low-rank matrices into the model architecture rather than adjusting all the parameters of the original model. Okay, I need to explore how exactly that is done. How are you introducing something into an architecture that already has something else built into it? Okay, how LoRa works. Freezing original weights. The original weights and parameters of the pre-trained model are frozen, meaning they are not changed during the adaptation process. Low-rank matrices. Small low-rank matrices, typically represented as a product of two smaller matrices, A and B. Oh shit, I missed the ad timer. Okay, there's going to be an ad playing in like, I don't know, 10, 15 seconds. Are added to each layer of the model. These matrices capture the necessary adjustments for the new task or dataset. These matrices capture the necessary adjustments for the new task or dataset. This approach significantly reduces the number of training. Back up, back up, back up. These matrices capture the necessary adjustments for the new task or dataset. Okay, that's an important thing. I need to figure out how exactly that happens. This approach significantly reduces the number of trainable parameters, making the training process faster and more memory efficient. Benefits: reduced computational cost. Oh, all right. So there's an ad playing right now. So I'm going to take a hydration break and I'll see you guys in 30 seconds. Okay, that must have been, I hope that was not loud on stream. I was closing my bottle back up and it made a sound. So yeah, cool. Welcome back. Welcome back from the ads. Where was I? Yeah, okay. Benefits. Reduce computational cost. By reducing the number of trainable parameters, LoRa drastically decreases the the computational resources and memory required for fine-tuning. For example, in models like GPT-3, the number of trainable parameters can be reduced by 10,000 times and GPU memory requirements by 3 times. No additional inference latency. Once the fine-tuning is complete, the low-rank matrices are merged with the original parameters, ensuring that there is no additional latency during inference. Application to transformer architecture. LoRa is particularly useful for large language models based on the transformer architecture, such as GPT-3, Roberta, dBERTA. GPT-3, Roberta, and dBERTA. By injecting low-rank matrices into each layer of the model, of these models, LoRa enables efficient task-specific adaptations without the need for full fine-tuning of the entire model. In summary, LoRa is a powerful technique for adapting large pre-trained models, especially those using the transformer architecture. By leveraging low-rank matrices. Hold on, sorry. As I was reading this thing, my mind just went all over the place. Especially those using the transformer architecture by leveraging low rank matrices to reduce the computational and memory requirements associated with fine tuning. Okay. So LoRa can also be used on other architectures like FCNN, CNN, and RNN, or is it mainly meant for transformer? Okay, while low rank adaptation is primarily discussed and applied in the context of transformer architectures, especially for large language models, it is not limited to this architecture alone. General applicability. LoRa can be applied to various types of neural network architectures, including but not limited to transformer, other. Okay, you can apply it to FCNNs as well. LoRa can be integrated into dense layers of FCNNs, into dense layers. Okay, I need to look into dense layers because I've only been adding linear layers. And I think dense layers aren't they a part of convolutional neural networks? I'm not sure. Okay, I'm gonna have to look into it. To adapt these models efficiently to new tasks or datasets. Convolutional neural networks. Although less commonly discussed, the principle of using low-rank matrices can be extended to CNNs, particularly in their fully connected layers or other dense components. RNNs. LoRa can also be applied to RNNs, especially in the fully connected layers or other parts of the architecture where weight matrices are used. Key considerations. Layer compatibility. LoRa is most effective when applied to layers that involve weight matrices, such as the fully connected layers in various architectures. It integrates seamlessly with these layers by introducing trainable low rank matrices without altering the fundamental structure of the original model. Efficiency and performance. The benefits of LoRa include reduced computational costs, lower memory usage, and okay, yeah, that's fine. Okay, cool. Um, I'm learning deep learning, PyTorch, and neural networks. Let's add about in there. About deep learning, PyTorch, and neural networks. I've seen. Oh, actually, deep learning. Actually, let me add data science in there. Data science, deep learning, PyTorch, and neural networks. I've seen the term sparse pop up quite a bit. Well, not quite a bit, but like I'm just gonna say quite a bit. Pop up quite a bit. I'm wondering what that means in these contexts. Because I've seen stuff like sparse matrix, for example, and when I looked into that, what I found out is that the idea behind a sparse matrix is that it's a format that stores a matrix without the zero components, or I guess you can like substitute a specific one, but in this case I guess it's just zero, but maybe they have methods to choose a specific number that you're just not going to include, and so it stores the matrix without including the zero component. So if it's a 2D matrix, let's say a 4 by 4 matrix, and let's say four of the cells in the matrix are zero, then it's not going to store 16. It's going to store 12 of those cells. That's what I've understood so far, but that was about sparse matrices. I don't know if my understanding about it is correct. I haven't played around with it enough. It's just bookish knowledge that I have so far based on the research that I've done. But like I've seen the term sparse being mentioned in a bunch of different places, so I need to understand what sparse means here. In the contexts of data science, deep learning, and neural networks, the term sparse refers to data or model parameters that have a majority of zero or near zero values. That's interesting. They have a majority of zero or near zero values, with only a few non-zero elements. Okay, here are some key aspects of sparsity in these fields. Sparse data. Definition. Sparse data is characterized by a high number of zero or missing values. For example, in a movie rating data set, most users have most users may have rated only a few movies, resulting in the matrix with many empty cells. In a matrix with many empty cells. Challenges. Sparse data can lead to overfitting as models may struggle to generalize well from limited non-zero data points. It can also make models more complex and harder to train. Sparse representation. This refers to the encoding of information where only a few elements in the representation vector are non-zero, while the majority are zero. This is useful in deep learning as it leads to more efficient computation, reduced memory usage, and helps in identifying the most important features of the data. You have sparse uh, parameterization and sparse representation. Okay, so weight sparsity occurs when most of the model parameters weights are zero or near zero. Techniques like L1 regularization can enforce this sparsity. Activation sparsity refers to the case where the activations, uh, which are outputs of the hidden layers of a neural network, are mostly zero, meaning only a few neurons are activated for any given input. Benefit of sparsity, efficiency. So, okay, all right. So here they are mentioning that sparse data is data that's mostly zero and only contains like a few non-zero elements. So it's either zero or near zero data. But then, in summary, sparse data is so and so, so and so, so and so. Okay. Okay. I read up on sparse matrices. If your definition is correct, then explain to me why sparse mat did I spell that? Yeah, I spelled that wrong. Why a sparse matrix is a matrix where the zero values are not stored. Okay, a sparse matrix is still considered a matrix even though the zero values are not explicitly stored due to several key reasons and efficiencies in its representation and operation. Uh, Representation efficiency. In a sparse matrix, only the non-zero elements are stored, along with their corresponding row and column indices. This approach significantly reduces memory usage as storing all the zero elements would be wasteful and inefficient. For example, in a movie rating matrix, where most of the users have rated only a few movies, storing all the zero ratings would consume a lot of memory unnecessarily. Data structure. Sparse matrices use specialized data structures such as compressed sparse row, compressed sparse column, dictionary of keys, and list of lists, and others. These structures are designed to efficiently store and manipulate the non-zero elements, effectively representing the matrix without the need to store zeros. Conceptual integrity. Despite not storing the zero values explicitly, the sparse matrix still maintains the conceptual structure of a matrix. It retains the row and column indices and the relationships between elements, allowing it to be treated as a matrix in mathematical and computational contexts. The sparse representation is merely an efficient way to handle the data without losing the essential matrix properties. So if I'm understanding this correctly, a sparse matrix is a matrix where only the non-zero elements are stored, but sparse data is data that mostly contains zero elements. Is that right? Uh, okay. Sparse matrix. A sparse matrix is a matrix where where most of the elements are zero, but only the non-zero elements are stored along with their corresponding row and column indices. This efficient storage method reduces memory usage and improves computational efficiency by avoiding the storage of zero values. Sparse data. Sparse data refers to data sets where most of the elements are zero or empty. This type of data is common in various applications such as NLP, where most documents do not contain most words, recommendation systems, where most users do not no, have not rated most items, and network theory, where most nodes and not connect what? Where most nodes are not connected to each other. Okay. Key points. Yeah. Okay. That's cool. So I'm just gonna ask a silly question here. Isn't this a bit of a juxtaposition? I kind of need to ask this question so that I'm able to connect the dots in my mind, and so that the doubt will be clear in my mind. This is one of the reasons why I like LLMs so much, is because they won't get mad at you when you ask questions over and over again and you keep asking for clarification because you haven't understood the concept, or if you have questions that would be considered silly, but it's in reality is just you being curious. uh, they're not going to get mad at you. Okay, the concepts of sparse matrices and sparse data, while related, serve different purposes and are not inherently contradictory. Here's a clarification to address a potential juxtaposition. Sparse matrices. A sparse matrix, I get that. Okay. The term sparse matrix refers specifically to the storage and manipulation method, not the inherent nature of the data itself. Okay, sparse data. I know what sparse data is. When dealing with sparse data, using a sparse matrix representation is often beneficial. Wait, I should have read the first point because I thought it was just explain. Okay, sparse data, on the other hand, refers to data sets where most of the elements are okay. All right. This is a characteristic of the data itself rather than a method of storage or manipulation. Okay. All right. So there was something wrong in what I was trying to compare. These are two different things. Okay, when dealing with sparse data, using a sparse matrix representation is often beneficial because it aligns with the nature of sparsity of the data, allowing for efficient storage and computation. Alignment and efficiency. The use of sparse matrices for sparse data is not a juxtaposition, but rather a harmonious alignment. Sparse matrices are specifically designed to handle sparse data efficiently, making them a natural fit. By storing only the non-zero elements, sparse matrices leverage the inherent sparsity of the data to reduce memory and computational requirements, which is particularly important when dealing with large data sets. All right. Yeah, I can see that being a thing, at least with large data sets. Um, I don't know about like the tiny data sets, like really, really small matrices, but as the matrix or even like the data set in general, maybe it's a multidimensional matrix, as the matrix becomes bigger and bigger, as the data set becomes bigger and bigger, we're talking about like, hundreds of thousands of rows and columns and, more depending on the dimensionality of the matrix. Um, I feel like only storing the indices of values that are not zero, like as if it is a matrix that has a whole lot of zero values, then only storing the non-zero values, the indices of the non-zero values, that would end up being a lot more cheaper, a lot more efficient, at least storage wise. And then you can you can load it up and reconstruct the matrix as a full matrix and fill in all the zeros that you need to fill in when the time arises. Though I wonder if there are mechanisms for working with sparse matrices, like as they are, without having to reconstruct an entire matrix, because it did mention memory efficiency and stuff like that. So maybe when it's dealing with sparse matrices, it's somehow able to take into account the zero values, while also um, while also looking at the actual stored data, which is non-zero values. But I'm curious as to how it's able to use how various methods and algorithms and stuff would be efficiently using the matrix if the matrix has to be reconstructed. Like, are they not reconstructing the matrix? Um, have they found a more efficient way of doing the calculations using only the data that's stored in the sparse matrix without having to reconstruct an entire matrix filled with like empty values? Because like those empty values, they even though they are empty values or zero values, they're part of the data set. they they sort of form, or how do I say this, in many ways they would give the data set its meaning, its pattern. It's not just the non-zero values, even the zero values, the zero and non-zero values together make up the data set, and together they make up whatever pattern you're going to make up from visualizing the data set. Yeah, I'm curious about how sparse matrices get handled in memory, not during storage. Because I can imagine a way to store them efficiently, but like I'm wondering if there's a way. I'm sure there must be a way. I just need to look into it. But yeah, I'm wondering if there's a way that these matrices are stored in memory in What am I trying to say? I'm wondering if there's a way that these matrices are stored in memory such that they would uh, still be useful in various algorithms without having to generate an entire matrix of the original shape out of them. Because that would be truly memory efficient. But I'm not entirely sure to what extent like that to what extent it only uses, the non-zero data. Because in some cases you kind of need the zero values as well. Um, just so the data that you're passing in, it has a certain kind of meaning to it. It has a certain kind of, like, it's one of those things where I don't even know how to explain. It's making sense in my head, but like if I try to explain it, it's not making it's not going to make any sense. But okay, I get it now. Cool, great. So what were we supposed to be? Oh, I need to add these things to the list. What all was that? Nano Sparse Attention. I think I should put that under transformers. Yeah. This can be at the bottom. Nano Sparse Attention. And I think LoRA can also come under this. I think LoRA can also come under this. Because while it's mainly being applied to, though, I mean, they did mention that it can be applied to, um, they keep mentioning specifically the fully connected layers, meaning they can definitely be applied to feed forward neural networks. So you know what? We're gonna make that its own separate thing. Okay. Um, just a second. All right. Okay. Great. Okay. Here's what I'm gonna do. I'm gonna switch to BRB real quick. I'm gonna get up and walk around and do some physical activity because I've been sitting for an hour and that's not good. So, well, it's not good for me. So, um, I'm gonna get up and walk around and stuff, and then I will come back and we'll continue. It's just gonna be a couple of minutes. So I'll see you guys in a couple of minutes. I'll switch to BRB, I guess, and I'll mute my mic, and then I'll come back. All right, we are back. So, uh, here's what I'm thinking. Now, there's one of two things that I could do. By the way, this thing that I was showing you guys yesterday, which I ended up not doing, which I was initially planning on doing on stream, but I decided not to do it because I couldn't think of a whole lot of ideas. It's kind of weird. It was like, okay, prior to the stream, I was like, yeah, sure. During the stream, I'll come up with various ideas to explore this data set. And then during the stream, I was just blanking on ideas, different things that I could, because there's so much that I want to explore in this small data set. This small data set, just, sort of a recap. This small data set contains prices. It's sort of a trading data set. It contains the trades that a trader has made where they bought a certain asset at a certain price, or rather, I should say, they bought a certain amount of an asset at a certain price by spending a certain amount of money. So, to calculate, to do the calculation is basically total amount of money that they want to spend divided by the price, and that gives them the amount of the asset that they're going to get for that price and for the amount of money that they're willing to spend, or at that price for the amount of money that they're willing to spend. And just like that, we have multiple different price ranges and multiple different amounts of money that they have spent. And so they've bought this asset at different points in time at different prices, with different amounts of money. Right? So we have these three rows, which is the prices, the amounts, and the totals. And initially, what I was doing, so the initial thing that I was trying to find out here was I was trying to run calculations for dollar cost averaging, which is basically where you buy assets at fixed intervals. You buy fixed amounts of the assets at fixed intervals. And in the end, when you sell it, supposedly the highs and lows, they balance each other out to a certain, to the point that you are able to make a profit, right? But I was like, okay, rather than just heading into it blindly, let's try and find out the exact point above which you would actually make a profit. And it turns out that the exact point above which you would make a profit is the average of all of these prices. So you take all of these prices and you calculate the average of these prices, and you need to sell above that average price to make a minimum profit. Obviously, if you sell higher than that average, you'll make much more profit. But that average is your, I'm not sure what to call it, but that's your line. That's your red line. Selling below that means you're gonna make a loss. Selling above that means you're gonna make a profit, and that's fine. That's great. But I wanted to try and play around with this data more and do various things with it to try and experiment. Like one idea that I had, which I didn't go ahead with it because we ended up moving on to a different topic yesterday on stream. But what I wanted to do was I wanted to try and scale down the prices, the totals, and the amounts all together, and scale it down using the standard scaler in scikit-learn. And then I wanted to try and plot them to see if they still maintain their shape, maintain their patterns, and more importantly, and I wasn't sure how I was going to test this part, but more importantly, I wanted to see if they're able to maintain their relationship. I'm still not sure how I would have gone about testing for that. But yeah, I wanted to see how well they would maintain their relationship. And then yesterday, or I think today, yesterday before I fell asleep, I forgot to write the thing down because I suddenly got the idea when I was about to go to sleep, and then I didn't write the thing. But another idea that I got for stuff that I can do with this data set is trying to figure out if multiple small amounts or multiple small totals would give you a better chance of making a profit, or lesser big totals would give you a better chance of making a profit. Because it kind of feels like the more you spread out, um, the amount, or rather I should say the more trades you are making, the more you're able to spread out the risk. But I need to figure out to what extent that really, how do I explain what I'm trying to say? I need to figure out to what extent that works, to what extent um, that works out in the favor of the trader. And this is all just like a scenario that I'm building up, but like I got this idea and I kind of want to go ahead with, trying to figure out this calculation, because I feel like I figured like um, this is a fun data science related problem, a fun stats related problem, because it's less about the trader making the trader making profit is just, it's part of the scenario. But what I'm trying to figure out is, or rather what I'm trying to do is use this data and try to find patterns in this data. I still don't know what types of patterns I'm looking for, but I want to see what I can find, and that's why I'm trying to visualize this in different ways. Maybe once I've looked into more methods on scikit-learn, then I can probably try and apply them to this. But yeah, so I'm this is something that I'm going to be doing on in my own time, maybe not on stream. For now, what we could do is, so I had two ideas. One is I could either go ahead and build another feed forward neural network from scratch. So we'll kind of get back to, you know, doing neural network stuff. And two, I could carry on learning about Hugging Face transformers. And this time we're going to be starting the next page, which is running inference with pipelines. You know what? I think we'll do this. Let's see how far down we're able to get. I don't know. I don't know if we're gonna finish the entire thing. They are exploring, I think, different. I think they're exploring different modalities. So, dude, okay, hold on. So I've used the term modality. I've heard of the term modality, but I have a question which I think Llama can answer. So, in terms of, wait, I'm learning to use Hugging Face transformers, and I've learned that there are, or rather, I should say, I've learned about the term modality. Uh, does this term have to do with the word mode or model? Because I feel like it has to do with mode, but if it does have to do with model, then I would like to figure out what the actual meaning of model is, at least in this context. Okay, the term modality in the context of Hugging Face transformers and multimodal learning does indeed have a connection to the concepts of mode and modal, although although it is used in a more specific and nuanced way. Modality as a medium or mode. In this context, a modality refers to a medium or a way in which information is presented or perceived. For example, vision, text, and touch are all for example, vision, text, audio, and touch are all different modalities because they represent different ways in which data can be expressed or sensed. Etymological connection. The word modality is derived from the Latin word modalitas, which means the state of being modal or a mode of being, the state of being modal or mode of being. In in philosophy and logic, modal refers to modes of existence, necessity, or possibility. However, in the context of multimodal learning, the term modality is more about the different modes or channels through which data is communicated or perceived. Okay, so that's one of the reasons why I was like, I'm leaning more towards it being mode, but if it's modal, then I would like to know exactly what modal means here. Um, because mode, the way I was imagining it was more like, okay, text mode, audio mode, and stuff like that. Because like for these different types of models, you give them input in different ways. If it's a text model, you can't really give it audio input and expect it to work, and vice versa. And also the same for vision models. Like each of these models, they do different things and they expect different types of inputs. So I was connecting mode to that. And to be honest, I've seen modality being used in that context, in that way, quite quite often. When they say multimodal model, they are often saying that you're able to provide it input in different modes. Uh, okay, did I finish reading this? Yeah, okay. So, practical application. In multimodal learning, each modality, image, text, audio, etc., brings unique information and strengths. Combining these modalities can enhance the overall understanding and performance of models by leveraging the complementary nature of different data types. In summary, while the term modality refers to an etymological connection, no, shares an etymological. I've been saying etymological. It's etymological. Why did I say entym? What is entomology? And what is etymology? Oh, am I okay? Wait, let's. Am I like confusing these two things? Are entomology? That's not a word. Okay, so this thing is going to correct me. I shouldn't call it a thing. Llama is going to correct me. So are entomology and etymology the same? Is entomology even a word? I feel like I've heard it before. Entomology is not a recognized. Okay, hold up. Entomology is not a recognized word in the English language. The correct term is etymology. Why do I remember entomology then? Um, where do I remember entomology from? I don't know. Okay, anyways, etymological connection. The word modality is derived from the Latin word. Okay, hold up, back up. Practical application. Uh, where was I here? Combining these modalities can enhance the overall understanding and performance of models by leveraging the complementary nature of different data types. In summary, while the term modality shares an etymological connection with mode and modal, its used its usage is its usage in multimodal learning is specifically about the different mediums or channels through which data is represented and processed. I just realized that I don't think I understood what modal means here. Did it mention what modal? Okay, modal refers to modes of existence, necessity, and or possibility. Uh, However, in the context of multimodal learning, the term modality is more about the different modes or channels through which data can be communicated through which data is communicated or perceived. All right, great, cool. Where was I? Oh yeah, we were looking at. I was talking about multiple modalities in these models or in these different tasks because they have different tasks and each task has different models with different modalities, and they also have multimodal tasks which or well multimodal models that fall under certain tasks, which I don't think I've looked into those yet. I need to look into those because there has to be a certain amount of like if we're talking about multimodal models that accept input in different forms, there have to be multiple models in that one model, right? Either that or regardless of the type or no, depending on the type of information that's passed in, depending on the mode that's used, the input mode, um, the data is processed in a specific way, and then it's just one model that's used. But I don't think it's one model. I think it's three different models that are built to handle three different types of data. Another good approach, which probably wouldn't require multiple models, is if they found a way to standardize the data. Um, standardize the data to one given format, regardless of what the input mode is. If they found a way to standardize the data while also maintaining the important features in the data, the important information that the model requires, then they could still use one model. I'm interested in learning about like how the multimodal models are working. Okay, multimodal pipeline. The pipeline supports more than one modality. For example, a visual question answering task combines text and image. Feel free to use any image link you like and a question you want to ask about the image. The image can be a URL or a local path to the image. Oh yeah, yeah. Okay, so this thing is just showing us how to run inference. It's running us through the entire pipeline process, and so it's probably going to teach us about like the multiple modalities and the different types of data that each modality uses. Because I remember I had this issue in what was it? I think it was in sentiment analysis, where yeah, sure, you could one very easy method thanks to Hugging Face, thanks to the devs of transformers. One very easy way to use the model would be to just call the pipeline object as a function. Like, of course, after you've instantiated it, you call that object that you've created as a function, and you pass the input in, and then pipeline is going to handle everything else for you behind the scenes. It does all the stuff that needs to be done, and then it gives you the output, and you're good to go, right? Another way to go about it is if you want to have a little more control over the workflow and over what exactly is going on and the various pieces being used. Then you can specify the tokenizer yourself and specify the model yourself, and then you pass the input to the tokenizer. You get all the IDs. You then pass those IDs um, to the model. The model does its analysis, and it gives you the output of the neural network, which has not yet been run through a softmax function. So you need to then run the logits through a softmax function, and then you get your probabilities. Why was I saying this? Oh, yeah. So I think this page is probably going to cover those things. It's going to teach us, hopefully, it's going to teach us in different modalities how you're supposed to handle giving it input. Let's take a look at the other. Okay, so there's writing portable code with auto class. Then there's pre-processed data, and then fine-tuning a pre fine-tune a pre fine tune words. Holy shit! Fine-tune a pre-trained model. There we go. Fuck me. Um, Fine-tune a pre-trained model, and then there's also train with a script, which I remember reading something interesting about that. I don't know, I don't remember what it was, but there was something that I found really interesting about train with script. So there's gonna be some reading. We're gonna be doing some reading. Um, right. Okay, let's start reading. The pipeline makes it simple to use any model from the hub for inference on any language, computer vision, speech, or multimodal tasks. Even if you don't have experience with a specific modality or aren't familiar with the underlying code behind the models, you can still use them for inference with pipeline. This tutorial will teach you how to use a pipeline for inference, use a specific, oh, sorry about that, use a specific tokenizer or model, and use pipeline for audio, vision, and multimodal tasks. Take a look at the pipeline documentation for a complete list of supported tasks and available parameters. Okay, let's try searching. The task defining which pipeline will be returned. Okay, so is this the list of tasks? I think so. Fill mask and oh, this is interesting. Okay, so there's a lot of them here. Is there like a list where these things are explained further? Oh, wait, no, there's a separate pipeline for each of them. So depending on what task you select, it's gonna return the specific type of pipeline. All right. What is fill mask? Let me look that up. Uh, is this part of NLP? Oh, it's part of NLP. Okay. Masked language modeling prediction pipeline using any model with LM head. See the masked language modeling examples. Let's take a look at that. Oh, you know what? Let's try asking here. I'm learning HF transformers. In the pipeline object, I noticed one of the tasks is called fill mask. What is that? Also, while this does its thing, there's going to be an ad playing. I mean, the ad timer is about to run out, so I'm going to start the 30-second ad right now, and I'll take a little hydration break. So by the time you guys come back, this answer should be ready and the ad should be over as well. So I'll see you guys in 30 seconds. All right, welcome back. This thing is, shouldn't be calling it thing. Uh, Llama has given an answer. Let's read it. Okay, in the context of Hugging Face transformers, the fill mask task is a specific application of masked language modeling. Here's a detailed explanation of what it entails. Masked language modeling is a training technique where some of the words in a sentence are randomly replaced with a special mask token. The model is then trained to predict the original word that was masked. This approach helps the model understand the context and relationships within the language. So the idea is that we remove certain words from the sentence and then we get the model to guess what the words might have been. And it being able to guess accurately shows that it is able to understand the context and, well, it's saying the relationships within the language. I'm assuming relationships between like the different words that are being used in the language. It, yeah, yeah, I think in a way, yeah, that's true. That would show like a better understanding. Dude, hold on. Just a second. Just a second. Um, I need to mute for like a minute. I'll be back. All right. I'm back. So let's continue. Okay, fill mask pipeline. The fill mask pipeline is a pre-built functionality in the Hugging Face Transformers library that allows you to use a pre-trained or fine-tuned model to fill in the mask tokens in a given text. Here's how it works. Input. You provide a text with one or more mask tokens. Processing. The pipeline uses the model to predict the most likely words to replace the mask tokens, and output. The pipeline returns a list of possible fillings for the mask tokens ranked by their probability scores. Okay. Mask filler and so and so and so and so. Okay, so this is using. Oh, wait, it's giving some more information here as well. Wait, let's see what the thing does in action. Okay, so Paris is the mask of France, and then it replaces it with one with. Oh, it's giving you like the entire sentences, and it's giving you probabilities of which one it is most likely to be. So prediction, basically. It's predicting uh well, predicting, or would it fall under classify? Nah, it's more predicting. It's predicting the probability of one being the answer. Okay, key features. No labeled data required. Masked language models do not need labeled data for training, making them practical for domain adaptation and pre-training on large corpora. I think it's corpora. I'm not sure. Okay, let's say corpora for now. Domain-specific training. These models can be fine-tuned on domain-specific data um, to improve performance on tasks such as text classification, question answering, or information extraction within that domain. Customization. You can specify the number of predictions to return using the top K parameter and oh, okay. You can specify the number of predictions to return using the top K parameter and even limit the predictions to specific target words if needed. All right, great, cool, awesome. Right. So we can carry on with this. So pipeline usage. Wait, what other tasks are available here? I'm interested in checking out the image related pipelines, more specifically something like image to image, because I wonder if we can do something like um, I don't know, giving it an image and it can read the style of the image and then generate another image in a similar style. And I mean there might be like I can combine multiple different because like dude, one of the reasons I really like uh, transformers or Hugging Face transformers library specifically, I've mentioned this before. It's that it creates a sort of abstraction layer. A good example is what Llama gave us over here. I think. Look at this. Three lines of code. Well, four lines including the import line, but three lines of code. Um, you create the pipeline object, you specify the task, and then you call the pipeline object as a function and pass in your input, whatever input it's expecting, and then you get your result. It's that simple. And you can also, there's also a more complex way where if you know what you're doing, if you know what kind of model it is, what kind of input it requires, what the different moving pieces are, and what inputs they require, what outputs they give out, and how to connect them all together. If you know how to do all that, you can definitely you can definitely go about it in that way as well. You're not limited to just this abstracted way, but this abstracted way makes things a lot more accessible, especially if you're trying to build like higher level things using multiple different pieces, multiple different models. You don't necessarily need to worry about the implementation details of every single model. Of course, once you start doing more complex things, to a certain extent you're going to have to worry about it, but like as general usage, um, not having to worry about the implementation details and what to input and what the output is and how the various pieces are working together, not having to worry about all of that stuff, it can allow you to create much more high level things using these various pieces. The various pieces in this case being the different types of pipelines that you can create using the different tasks. Text to text. Okay, I'm curious about what table question answering is, because there's a question answering thing as well. What is table question answering? Table question answering pipeline used for a model for so and so. The pipeline is only available in PyTorch. Oh, okay. There's no TensorFlow version of it. Okay, hold on. Okay, all right. Um, what is table question answering? Uh, okay. Table question answering is a task in natural language processing that involves. Give me a second. All right. Table question answering is a task in NLP that involves asking questions based on the information presented in a table. Here's a detailed overview of what it entails. Table QA is the process of answering questions about information contained within a table. This task requires the model to understand the structure and content of the table, as well as the natural language question being asked. Process. Here's how it typically works. Input. The model receives a table and a natural language question related to the table. Processing. The model analyzes the data and the question to identify the relative parts of the table that can answer the question. This may involve semantic parsing, where the model translates the natural language question into a logical form that can that can be executed on the table data. Output. The model returns the answer to the question, which can be a simple value, a set of values, or even the result of an aggregation function, sum, average, etc., on the table data. Examples. For instance, if you have a table with columns for country, GDP, population, and you ask the question, what is the total GDP of China? And so, okay, this is useful. I need to find out which different models are available for this kind of thing. You know what? Let's look it up right now. So let's look for the task specifically. Um, Table question answering. And okay, so Google has one, Microsoft has one. I was just looking at another one, which was by who? Mina. Okay, cool, cool. Table question answering. Tapas large, fine-tuned, so and so. Okay, so this seems to be the latest one from Google. And then, okay, a bunch of these are from like a year or 2 or 3 years ago. Okay, let me try asking a question here. Wait, models and techniques. Several models and techniques are used for table QA, including table parser, a pre-trained model by Google that is fine-tuned for table question answering. It can perform operations like summing or averaging values based on the question. Semantic parsing. This approach involves translating the natural language question into an SQL query that can be executed on the table to retrieve the answer. Retriever models. In some cases, especially when dealing with large language model, no, when dealing with large number of tables, retriever models like MPNet are used to first identify the most relevant tables and then pass them to a table reader model for final extraction. Use cases. Table QA has various use cases such as simulating SQL execution and complex question answering. Yep, true, true. Dude, in the past, I'd been looking for this kind of a model. Um, but like by that point, ChatGPT had already come out. Not only had ChatGPT already come out, but I think it had already um, had the ability to analyze files put into it or built into it. Like this wasn't like immediately after ChatGPT came out, but like soon. I think it was a couple months later, or maybe a year later or something, OpenAI had announced that, yeah, you can now upload files and it can analyze the data for you. And then you can ask it questions. You can ask it to do data visualization for you. You can ask it to do data processing in various ways, retrieve data and all of that stuff. ChatGPT is essentially it's a multimodal model, right? You can use it in many different ways. It can do many different things. It can give you different types of outputs as well. But I didn't want to use ChatGPT. I wanted to see what other tools are available for doing this kind of thing. And I guess at the time I just didn't look up the right term. And it seems like table question answering, it seems to be the closest thing to what I'm looking for. Because like I'd imagine, or well, I'm currently imagining a situation where we pass in a pandas data set to the model, and the model then analyzes this, and we can ask it questions about the data. That can be super useful, because just as an example, because we would have to find a way to use this along with a bunch of other models, because currently talking to LLMs, it how do I say this? The context doesn't live very long in the LLM's head. The context doesn't live very long. As you keep having the conversation with the LLM, you'll notice that it starts to forget what you were talking about initially. And it's subtle. It's not like it's going to happen all of a sudden, but you'll slowly start to notice in the way that it's talking, that or with the replies that it's giving, you'll start to notice that, oh, it's kind of forgetting what we were originally talking about. It's kind of lost the context. So in this case, I wonder if, though, I mean, to be fair, in this case, I don't think it's going to be us having like, a constant conversation with the model. It's going to be like a one shot kind of thing. So you pass input to it and you ask a question, and then you get the answer. And then you pass input again, you pass the same input again and ask another question and get another answer. Or you can just pass it input and then ask a bunch of questions and get a bunch of answers about the thing. So I don't think they're necessarily comparable. I don't think I was comparing. I was just saying that, like, in when you're trying to do this with an LLM, it can get a little bit complicated. Though I feel like that situation has improved now, in the sense, not necessarily LLMs have become better at it, but we have other tools, stuff like Notebook LM, for example. You can feed it some kind of input, like maybe a PDF or an HTML page, or I don't remember all of the inputs that it accepts. I think it also accepts a YouTube video. I think it reads the transcript of the video, or it finds a different way of studying the metadata and the data of the video itself. I'm still not sure about how it's studying the data of the video, because in the past it was looking into the transcripts. Now I don't know what other method it has, but yeah, Notebook LM does have multiple different ways to give it input, and you can give it input. Let's say you give it, I don't know, what good example should I give? Let's say you've given it a PDF file containing some information, and let's say that the PDF file contains a bunch of information, right? Lots and lots of information about a specific subject. You can then ask Notebook LM to summarize the all of the data for you, or give you like specific important points, or you can ask it questions about this data that you've just fed into it. So yeah, I mean, we do have a bunch of much more sophisticated tools now to use. Either way, carrying on with this. Um, complex question answering. Models can handle complex questions that require multiple steps or aggregations, making them useful for real-world applications where users need to extract structured information from tables. Datasets. Several datasets are used to train and evaluate table QA models, including wiki table answers, wiki SQL, and sequential question answering datasets. These datasets provide a variety of questions and tables to help models learn how to handle no to help models learn to handle different types of queries and table structures. Okay, cool. Oh yeah, I was gonna ask it this question. I'm looking at table QA related models listed on the HF hub. A bunch of them seem to be from 20, 2023, 2022, 2021, and earlier. We are currently in 2024. I'm wondering if other methods have been developed to solve or to handle table QA, because of which more table QA models aren't actively being developed. So, a couple of things here. I know that there are other methods. I just mentioned there are other methods, and I don't think that there aren't any models actively being developed. I'm still asking the question in that way, because I'm pretty sure somebody is working on something for a very specific purpose. Who knows? Maybe I could fine tune one of the existing models for a specific purpose. That could be a thing. Okay. While the models listed on the Hugging Face Hub may seem to be from earlier years, it does not necessarily mean that the development of table QA models has slowed down or ceased. Here are some points to consider. Ongoing research and development. Table QA remains an active area of research, I'd imagine, yeah. And recent advancements continue to enhance the capabilities of of LLMs in handling tabular data. For instance, the introduction of benchmarks like TableBench, as mentioned in the recent research, indicates ongoing efforts to improve table QA capabilities, especially in addressing the complexity of real world challenges of tabular data. New benchmarks and datasets. The creation of new benchmarks such as TableBench, which include 18 fields with 4 major categories of table QA capabilities, suggests that there's still strong focus on improving and evaluating table QA models. These benchmarks help in identifying the gaps and challenges in current models, driving further research and development. Advanced training methods. Recent studies have shown the potential of using in context learning, structure aware prompts, and step by step reasoning processes to enhance the performance of LLMs on table QA tasks. These methods continue to be refined and applied to new models, indicating active development in this area. Integration with other techniques. Table QA models are increasingly being integrated and integrated with other advanced technologies such as augmented aug, such as augmented analytics, real-time data processing, and AI-driven tools. For example, tools like Tableau and Power BI. I've heard about both of these tools when I was looking into data visualization and data analysis with Python. These are two of the tools that had been mentioned by people in addition to a bunch of other tools as well. I don't know if these are libraries. I don't remember if these are libraries or they're like their own standalone tools or their own standalone platforms. Um, Tools like Tableau and Power BI leverage AI to automate data preparation and discovery, which includes handling tabular data effectively. Okay, practical applications and industrial scenarios. The need for robust stable QA models in industrial scenarios remains high. The disparity between academic benchmarks and practical applications underscores the ongoing need for models that can handle complex reasoning and real world data challenges. This continues to drive the development of more capable table QA models, more updates and fine tuning. Even if the base models have been developed in earlier years, they are often fine tuned and updated with new data and techniques. For instance, dude, okay, real quick, I want to pause here because there's something there's something that I need to explore. I'm not sure like if I need to explore this on a per task basis or just in general, but there's something I need to explore in terms of how do I explain this? So there's this thing, right, where you develop a model and then you train it on certain data. You train it on very generalized data. And then that model can be fine-tuned for more specialized tasks. So that way you don't have to train a different model for each different task. You can train this one model with enough data that's generalized enough that it can be used for multiple different things, but then you fine tune it. So the model by itself cannot be used. I mean, it can be used, but like it's not necessarily going to give you, it's not necessarily going to perform well for like the special tasks. However, you can then fine tune this model. The model has been built in such a way that you can fine tune the model. Uh, you can fine tune the model so that it performs well in specific tasks. There's something that I need to explore here about what exactly is going on. I guess that's the best way that I can put it because I'm not sure how to explain what exactly I'm trying to explore. But it's this thing that I want to explore where you build a model and then train it on very general data. You train it on enough data that it can, you train it on data that you feel is generalized enough that it would be used in multiple different scenarios. Um, and then you still give it the capability to be fine-tuned, but the fine-tuning alone is not enough. Like it needs that generalized data, that general that very general knowledge, for lack of a better term, let's call it, that very general knowledge. You're building a model that has very general knowledge, and then you're fine-tuning it for specific tasks. This is something that I want to explore a lot more, and I want to see if I'm able to do this even with a simple feed-forward neural network. You know what? Okay, let's try asking Llama. So I've been learning. I'm gonna give it like a whole ass story here and see what it says. So I've been learning about deep learning, PyTorch, and neural networks. During this, I learned. Actually, wait, no. While learning about HF transformers, I learned that we have the ability to fine tune pre trained models, fine tune pre trained models on our own data so that they can perform well on specialized tasks. My knowledge of neural networks is limited to building. Actually, wait, no. Oh God, what just happened? What just happened? Oh, um, okay. Apparently, Control Shift X, it flips this thing. I've never done that before. Okay, cool. Right. So, um, where was I? Yeah. So, um, what I'm understanding from this is that, man, leave it up to me to just hit random ass keys on my keyboard. My God, dude. Yes. Okay. Thank you for that. Okay. From this, no. What I'm understanding from this um, is that the model is trained on general purpose data that can be applicable in multiple scenarios. But then we also have the ability to fine tune it for specialized tasks. I'm wondering, actually, no, I want to try and build a similar model, but my knowledge of neural networks is limited to. Oh, I want to try and build, well, I want to try and do something similar where I build a model that can be fine-tuned, but my knowledge of neural networks is limited to FCNNs so far. All right, so let's see what it has to say about this. Okay. Um, all right. Fine-tuning a pre-trained model is a powerful technique in deep learning that allows you to adapt a model on a that allows you to adapt a model trained on a large general data set to perform well on a specific specialized task with a smaller data set. Here's a step-by-step guide on how to fine-tune a model, even if your background is primarily in fully connected neural networks. Understanding fine-tuning. Transfer learning. Fine-tuning is a form of transfer learning where you leverage the knowledge gained by a model on one task to perform another related task. This is particularly useful when you have a limited amount of data for your specific task, but you can utilize a model pre-trained on a large related data set. Steps in fine-tuning. Pre-train a model. Start with a model that has been pre-trained on a large data set relevant to your dude, I wonder if a similar thing gets used in those platforms like character AI. Because like the thing with character AI is like you are able to, from what little I've used the platform, what I've noticed is that you are able to create. So I don't remember trying to create one, but I've tried using other people's created stuff. And at least from what I understand, you are able to create a sort of personality for the thing. Um, I think maybe you're able to specify stuff, specify like more details. I don't know exactly, but you are able to specify a personality for it. And my guess is that they're fine tuning the model. Fine tuning it how and like what kinds of data is being used. I'm yet to find that out. But this is my guess that they might be fine tuning the model so that it speaks in a specific way. Because you have like a whole lot of RP going on there, right? A whole lot of role playing. People will set up. People will set up like LLMs or bots of their favorite characters and then interact with them. I think you're also able to set up like role playing scenarios where you're able to like specify specify a scenario that's like being acted out, or an environment, I guess you can say. I'm not sure how like I'm not sure what exactly you're specifying there, but I've seen this stuff being like specific things you're able to do with it. Maybe I should explore character AI more and try to actually build something, because so far I've only seen stuff built by other people, and a lot of it was like game characters and whatever, anime characters and characters in general. And so they'll specify the kind of personality, and then they can chat with the person. I think they're also able to specify. I remember seeing a thing where you're able to specify a scenario, an environment, a scene, essentially, or a context, something that tells the LLM that, hey, in this current situation, this is what's going on. Um, I don't know the details around that though. Yeah, maybe I should explore. Maybe I should explore it more. Either way, I feel like fine tuning might be involved in that to a certain extent. Though you're spinning up a lot of different instances of these LLMs, right? I don't think like when you fine tune the model, it returns weights, doesn't it? It returns the fine tuned weights, and then those weights are what get used. I feel like that would be like storing that for each separate person would be very, very expensive. So there has to be a way to sort of create a sort of like plug and play kind of situation where you're able to plug um you're able to plug weights in. So like you have base weights, you have base you have the model's base knowledge, right? And then you're building stuff on top of that. The stuff that you're building on top of it, that is what you save. Everything else doesn't need to be saved, so you don't need to save the entire model weight, the entire model's weights each time. Just the specific fine tuning that you are doing. I guess I'm interested in finding out how you can create this sort of plug and play kind of thing. There has to be a way. I'm calling it plug and play, but like there's probably a way where you're able to pass in um, during inference. Maybe you're able to pass in something, or yeah, I'm not sure because it's not just one model, right? I'm trying to think of it in terms of scalability as well, because that's an entire platform. That's a platform with thousands, minimum thousands of bots running, right? Thousands of bots that have been fine-tuned in like different ways. So storing all of that can get expensive very quickly. Assuming they're storing, I definitely don't think they're storing um, all of the weights for every single one. Um, but because I don't think they're storing the weights for every single one, I think they're only storing like that small, that specific thing where you are the specific fine tuning parameters that you have specified. I think they're only storing that. But then how are they able to use it? Okay, I don't know. It's just something I'm curious about. Because like to be able to make it to it's one thing to build one model on which you can do this. It's another thing to make an entire scalable service. Like it's a different thing to make this model scalable to the point where people are able to spin up multiple instances of the model, and or multiple instances where you're running this model, and you're able to fine tune it as well, and then save the fine tuning settings. Okay, anyways, let's carry on with this. So pre-train a model. Start with a model that has been pre-trained on a large data set relevant to your task. For example, if you are working with images, you might use a model pre-trained on ImageNet. For text tasks, models like BERT or Roberta models like BERT or Roberta pre-trained on large text corpora can be used. Modify the model architecture. Remove the final layers of the pre-trained model, which are typically specific to the original task. Example: the fully connected layers that predict the classes in ImageNet. Replace these with new layers suitable to your task. I didn't think about this. I didn't think about so I was just thinking about fine tuning the parameters, right? I didn't think about changing the architecture itself. I forgot that yeah, that's a possibility as well. Um, replace these new layers. No, replace these with with new layers suitable for your specific task. For example, no, for instance, if you're doing a binary classification, you would replace the final layer with a fully connected layer having two outputs. Freeze initial layers. Freeze the weights of the initial layers of the pre-trained model. These layers typically learn general features that are applicable across many tasks. Example, edges in images or word embeddings in text. Freezing these layers prevents them from being updated during the fine-tuning process. Ensuring that the general features, I forgot about this part as well, that you divide it up into like multiple layers, and then each layer is doing a different thing. I guess one of the reasons I forgot was because I haven't yet done more complex things with feed forward neural networks, and I haven't even gotten started with convolutional neural networks and recurrent neural networks. Dude, we need to start dedicating some more time to these things so I can at the very least learn the architecture, and then in my free time I can just start building networks for doing various things. Yeah, you know what I could do? I could ask Llama for ideas, simple, very very simple ideas of networks that I could build for stuff, because I'm going to come up with my own ideas, and this is a good thing. My own ideas don't really fit. They're not within the box. My ideas are usually out of the box, and they don't necessarily always lead to something useful. It's just me messing around with the thing to better understand it. And that's useful. That's a good thing. But I want to do both of those things. I want to do my silly, goofy ideas, but I also want to do I also want to build the network to do something actually useful. Because doing the silly and goofy things, they kind of help me understand the ins and outs of things. And doing that with neural networks is definitely going to help me understand um, how various things react in different ways, and also how various things that make up the neural network work together. Give me a second. Okay. Uh, Freezing these layers prevents them from being updated during the fine-tuning process, ensuring that the general features learned are not lost. Train the new layers. The new layers, the ones you added, using your what? No, train the new layers, the ones you added using your specific data set. Since these layers are randomly initialized, they require a higher learning rate compared to the frozen layers. A common approach is to use a learning rate 10 times larger for the new layers than for the frozen layers. Optional unfreeze and fine tune. If you have enough data and computational resources, you can optionally unfreeze some or all of the pre-trained layers and continue training the entire network with a smaller learning rate. This allows the model to adapt more closely to your specific task, but requires careful tuning to avoid overfitting. Example workflow. Here's a simplified example workflow using PyTorch, assuming you are fine-tuning a pre-trained model for a text classification. So from transformers, BERT tokenizer, BERT model. Okay, all right. So we already have the model here, do we? Create a custom classification layer. So this is, all right, so this is one layer. This is an entire network by itself, right? Okay, this is an entire layer by itself. This is an entire network by itself. Replace the pre-trained classification head with our custom head. Okay. Freeze the pre-trained layers for param in model so-and-so. Param requires grad false. Okay. Oh, we are basically freezing all the parameters of BERT so that it doesn't store the gradients when calculating the loss. It doesn't store the gradients so that when we do back propagation, it's not going to back propagate all the way to these layers. It's just going to stop at, wherever at the beginning. Well, beginning? No. In the case of neural network training, it's at the end because it's like back propagating, right? So all the way from the end. Anyways, set the learning rate. Okay, great. And then train the model. Okay, okay. Oh, I don't think I got to this part where we were training using batches of data. Because I just started doing my own silly stuff with the neural network. And see, this is one of those things where like doing silly stuff has its merits, but then doing this stuff, doing the more important stuff or the more practical stuff, that also has its merits because that introduces me to this kind of stuff where we are training we are training the neural network on batches of data as opposed to the entire data at once. Okay, zero grad, cool, cool. Calculate the loss and then back propagate. Okay, all right, cool. Okay, then these are the key points. All right, cool, nice. Okay, so here's what we're going to do. Okay, give me a second. Um, just a second. All right. Uh, you know what? Yeah. Okay. So we are gonna raid a person. We're gonna raid a person named Hacking Tegan. Okay. So that's gonna be it for today's stream. I'm gonna try and stream again tomorrow. I'm gonna carry on with this. Maybe tomorrow we're gonna focus on neural networks. I'm not sure. I can't say for sure what I'm gonna be in the mood for tomorrow and what my mind is gonna just grab onto tomorrow. But yeah, today we made a bunch of progress. Um, yeah. I don't have anything else to say. So yeah, that's gonna be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.